Okay, so we will finish off the notes today. Just before we start Hess's law, or some reminders from Chem 1, what an extensive property and what an intensive property is. I will let you read that. You are smart enough to read. But I do want to bring up the standard states for sure. But basically, with standard state is what are they at room temperature, okay? So if you're looking at my periodic table, things in black are solids, the things in red are gases, and there are 2 liquids at their standard state, which is bromine and mercury. So there are only 2 liquids. So most everything is solid, and then the gases are pretty obvious. So that's what we mean at standard state. Remember, if it's a solution, it's 1 molar, and of course standard conditions are 1 atmosphere and 25 degrees Celsius, which is different than STP. I said it yesterday in the notes, but it's enough to reiterate because it's very important that when I am doing the standard enthalpy of formation, remember it is for 1 mole of compounds from its elements, okay? So that means you might have to balance some equations with some fractions to get those to work. And then the heat of formation in a free element in its standard state is 0. Why is it 0? Because it's not formed. It's already here when the world began, okay? All of the elements that are here were already here for however long the Earth is, okay? Old it is. Again, standard state, 25 Celsius, 1 atmosphere, 1 molar, okay? So Hess's law is when we take the change of enthalpy, delta H is the same, whether that reaction occurs in 1 step or several steps. It is not dependent upon the pathway that reaction took to happen. We call that a state function. It's not dependent upon how it got there. A real-world example of that is my daughters live in Dallas. There's a lot of different ways that I can go to Dallas. It doesn't matter how I got there. It matters that I went from Houston to Dallas. State function, I got to Dallas. Okay. The sum of delta H for each step equals the delta H for the whole reaction. So remember yesterday we said there were 5 ways that we could determine enthalpy. We said stoichiometrically. We said by calorimetry. We can add up the equations, Hess's law. We can also use this equation, which is the heat of reaction is equal to the heat of formation of the products minus the reactants multiplied by all their moles. That's what summation means. And then the last one that we'll do at the end is bond energies. So we're going to do these first, we're going to do this formula of products minus reactants, and we're going to do the Hess's law of adding up the reactions, which is my favorite way, by the way. It's like a puzzle. All right, so we're going to do exercise 8. And we have all of these heat of formations given to us, and then we have our reactions. And so we're going to use the data given to us to calculate that. So we're going to do products minus reactants. Okay, so delta H, I forgot to say I was going to write. I do that all the time. So delta H of reaction is equal to the products minus the reactants. So I have 1 mole of Al2O3, which is a negative 1676, plus, and then I have 1 mole of AlCl3, which is negative 704, plus 3 moles of NO, which is positive 90, plus 6 moles of water, which is a negative 242. So those are all my products, and then I'm going to subtract my reactants from them. Aluminum is 0, because it is an element in its standard state, plus 3 times negative 295 for the ammonium perchlorate. So I add up all the products and then I subtract from them the reactants, and I should get an answer of negative 2,677 kilojoules per mole of reaction. All right. You might ask about sig figs there, but I'm adding everything up there. Basically, I'm just adding and subtracting. So I'm not looking at maybe sig figs, but I'm looking at decimal places. And I have several things with 0 decimal places, so my answer needs to have 0 decimal places. So that's what I need to look at. Okay? Any questions on that, what I did there?
So let's just do it because it was an element?
Yes, remember elements in their standard state have a zero heat of formation. Okay, zero heat of formation. Okay? So I would like you guys to try, oh no, we'll do this one together because this one's a little bit different. Okay? So in this one, it's giving us the total delta H already. And if you read that, it's asking us to calculate the heat of formation for glucose. It does not give us that value. It gives us CO2 and it gives us H2O. And then it gives us the overall delta H of reaction by telling us that this reaction has plus 2,800 kilojoules. And that would be kilojoules per mole when we take it out of there. So our delta H of reaction is how much? Negative 2,800. And why did we make it negative? Because it's on a product, which means it's exothermic, which means it's a negative value. Okay, and that's going to be equal to our delta H of products minus delta H of reactants. And that's summation, of course. I never do those things very well. You can't even tell what that is. That's supposed to be a summation. That is some poor handwriting. Ooh, that's pretty good. Okay. All right. So plug in what we have. So we have negative 2,800 is equal to 1 mole times negative 1676. I'm sorry. Guess what? That's the previous problem. I was like, that does not make sense. Yeah, okay. That's the previous problem. Sorry about that. 6, let's try that again. 6 times negative 393.5 plus 6 times a negative 285.8 minus, well, oxygen is 0, and then plus X, because that's what we're solving for. Now, before we go on to solve this, because it's simple algebra, I think you can do it, I want you to look at your notes, and I want you to look at the water value we just used here and compare it to the water value we used in the previous problem. They're different. So one of the things that you need to pay attention to when you're doing these is using the right phase of water and the right value. Gaseous water has a different heat of formation than liquid water. So you need to make sure that you're looking at the right phase, okay? So that's just a little side note. So hopefully you can do simple algebra, and you get delta H is equal to a negative 1276 kilojoules per mole. So that would be the heat of formation for glucose. Anybody confused on that one, or you know why I did it that way? Okay. Then I believe that brings me, yes it does, to my favorite kind. These are my favorite kind to do. Do y'all remember these where you have to rearrange and maybe either multiply or divide by a coefficient?
I wish I did.
Yay! I love these. They're my favorite. They're fun. It's like a puzzle. Okay, so this is what we mean by a state function. So this time I don't have my heat of formations. I have some reactions, and I can manipulate the 3 different reactions to get this overall reaction right here. So that's what I'm trying to get to. So I'm going to look at these different equations, and I'm going to manipulate them to give me that overall equation. So I'm going to start with the first one, and I'm going to look at that one, and I see that it's H3BO3, and I look at what I'm trying to get to, and I need H3BO3 to be on the reactant side. So this is in the right order, but I need 2 of them. So I'm going to take this first equation and multiply it by 2. And whatever I do to the equation, I do the same thing to the delta H value. So I'm going to multiply it by 2, so I'm going to rewrite that, and I'm going to have 2 H3BO3 going to 2 HBO2 going to 2 water. You don't necessarily have to write the phases down, but I almost always at least write them down for water, because some reactions will have water changing from liquid to gas, and you have to pay attention to that. So I always just at least try to write water. Ugh, can't talk. Write water. It's hard to say. So then my delta H is going to end up being a negative 0.02 times 2, because I multiplied by 2. Now, I can look at the second equation. I'm not sure what I'm going to need to do with it, so I'm going to skip it for right now, because I can definitely see in the last equation that I need B2O3 to stay on the product side. So I know I'm not going to reverse the third equation, because that's the only place I have B2O3, right? But I have 2 of them, and I only need 1, so I'm going to divide by 2. So now I'll rewrite that, dividing everything by 2. So I will have 1/2 H2B4O7, 1 of the B2O3s, and half a water. So then I'm going to take that delta H, and I'm going to say 17.5 divided by 2. So now I'm going to go back to that middle equation, because I have some stuff in the second equation that I don't have in the overall equation, which is the H2B4O7. Okay? I have half of 1. If I look in the second equation, H2B4O7 needs to be on the product side so it can cancel out the one in the last reaction. So I'm going to reverse it, and I'm going to divide by 2, because I have only half of the H2B4O7. When I reverse this equation, what's going to happen to my sign? It flips, because the current way it's written, it's an exothermic reaction. If I reverse it, the reverse reaction is now endothermic. So I'm going to change the sign and divide by 2. So divide it all, reverse it, and divide by 2. So I should get 2HB2 going to half H2B4O7 plus half a water. So now that delta H is a positive 11.3 divided by 2. You don't necessarily have to write the positive. You could just write it as a positive. But when I've changed the sign, I like to write it as positive so I know that I did it. Okay? So I can say, hey, when I'm checking it, if I did something wrong, I know, hey, I did change that to positive. So now we're going to cross out anything that appears on opposite sides. And so the HBO2 goes away. Same on this side, same on opposite side. The H2B4O7 goes away. And then I'm going to write out what's left. And then all of my water is on the same side, so I'm going to add them together for a total of 3H2O. And then I'm going to do the math. And when I do the math, I get 14.4 kilojoules per mole of reaction, which would be an overall endothermic reaction. Fun, huh? Rachel does not look like that's fun. That's going to be on the video. Rachel's on the video. Okay, so now that brings us to bond energies. And bond energies is where you're going to screw it up. Just going to tell you that right up front. Maybe by telling you that, you won't mess it up. But bond energies are kind of like backwards. Because for Hess's law, we tell you summation of the adhesive formations of products minus reactants. Okay? But bond energies are different because we have to, unlike AP Bio tells you, because they're wrong, we have to put energy in to break bonds. So when bonds are broken, it requires energy. When bonds are formed, it releases energy. Okay? And so we have to do bond energies this way. So when we do bond energies, it's going to be bonds broken minus bonds formed. Okay? Which ends up being exactly opposite of the products minus reactants. And it ends up really being reactants minus products. But it's because we're not using heat of formation here, we're using the bond energies. How much energy does it take to break, and how much does it take how much does it give off when it forms? So it's backwards. So this is why you mess this up, because you get so used to saying, oh, products minus reactants. The bond energies is where you will usually mess it up. So pay special attention to it. So I'm hoping by maybe telling you this is where you mess up, you'll be like, I'm going to prove her wrong. All right. So I am going to let you do this one. So where is my remote? I'm going to pause the video for a moment. Someone remind me to resume query. So this is the answer, negative 554 kilojoules per mole. So this reaction would be exothermic overall, okay? But the breaking of the bonds is actually endothermic. So when you see a negative reaction, that just means that more, what this means here is that more energy was released to form the bonds than was required to break the bonds, okay? All right, so one more that you're going to try by yourself. And then make note of that in your notes, the 2 got left out on the balanced equation. Okay, so the 2 got left out, so add the 2 in. We discovered it after they all worked it wrong, and then they were like, where'd you get that 2? And I'm like, this got left out of your notes. Okay, pausing it again, and you all work that one. Negative 808. There. What? Okay, so I went ahead and drew out those Lewis structures so you would know, A, why did I put 4 in front of the carbon-hydrogen bonds? Because there are 4 carbon-hydrogen bonds in the methane. Oxygen is double bonded, and there are 2 of them. And then carbon dioxide is C, double bonded, oxygen on each side. And so you need 2 of those. And then water has 2 OH bonds in water itself. But then you have 2 waters, and so that's how you do that. Okay? Good job. Yes?
How do you determine single bond versus double bond?
How do you determine single bond versus double bond? Are you talking about for like CO2?
Yes.
Well, first of all, carbon always gets 4 bonds, with the exception of CO. That's the only exception. So carbon's always going to have double bond. Always going to have 4 bonds, and you only have 2 oxygen to give it, so it's going to do that. But when we get to the bonding unit, we'll do Lewis structures, and that will ring a bell. But usually you can look at valence electrons and match it up that way. But yeah. But I was hoping that y'all just remembered CO2 because we did it so many times last year. But I was not right. Okay. So that is the end of enthalpy calculations. So let's go over the summary real quick. Again, I'm not going to insult your intelligence by reading to you. Some of this I'm going to go over quickly. Some of them I'm going to say you should read that on your own. When I say you should read it on your own, you should read it and study it on your own. Okay? But here's the summary. Delta H is positive, it's endothermic, and we have heat added to the system, means it's going to show up as a reactant. Delta H is negative, it's exothermic, energy is lost, it's going to show up as a product. Nature likes things in its lowest energy state, so that's what it's going to tend towards. And then let's look at some of these things here. When we're talking about the vocabulary of these changes, in the thermochemistry unit, a lot of phase changes are happening. When we are talking about phase changes, please, for the love of cheese and crackers, don't ever say that you're breaking a bond when you're doing a phase change. You are disrupting or overcoming intermolecular attractions or intermolecular forces. I can't tell you how many times that they've told us that at AP classes, that kids are still saying that when water boils, you're breaking the bonds. Okay, you're not breaking the bonds. You are disrupting or you are overcoming the intermolecular forces. And if you can say what intermolecular forces you're overcoming, all the better. In case of boiling water, you would be overcoming hydrogen bonding. Right. Okay. Freezing, condensation, and deposition, which is the opposite of sublimation, release energy. So if they're releasing energy, what are they? Exothermic. Fusion, which is melting, vaporization, and sublimation, I have to add energy into the system to get it to happen. So they are endothermic. So I can't tell you how many times people tell me that boiling or vaporization is endothermic because it got hotter. Well, why did it get hotter? We boiled it like we're boiling water. I turned on the stove and I boiled the water. So yeah, it got hotter, but it's because I added the heat. Okay. I'm going to say it again, right, big and bold and red. We are overcoming or altering IMFs. We are not breaking chemical bonds. Okay. There are some exceptions in the notes. Make sure you look at those. Okay. And then another thing is when you're writing these FRQs, is there a difference between a gas and a vapor? I mean, yes, but they're still gases, but we tend to not call something that is already a gas at room temperature a vapor. So like water vapor, because water's not a gas at room temperature, so we say water vapor. But we don't say oxygen vapor, hydrogen vapor. We call those gases. So don't look silly. Okay? The strength of the intermolecular forces, obviously if it's a stronger intermolecular force, it takes more energy to overcome them. So those are all the things, if it has a stronger intermolecular force, it tends to have a higher boiling point or a higher melting point because you have to overcome those intermolecular forces to make it melt. Okay. Generally, the more polar the molecule is, the stronger the attractive molecular force. Hydrogen bonding being the strongest of the intermolecular forces. Do you remember the three things that do hydrogen bonding?
No orange friends.
No orange friends. Although now that my daughter's at UT, maybe I shouldn't say no orange friends any longer. Maybe I'll say hydrogen bonding is fun. F-O-N.
Fawn.
Fawn. It's fun.
Fawn.
It's fun. Yeah. Yeah. Okay.
It's like
And then
Sears child.
if you're in physics, you recognize this.
That's upsetting.
It's not upsetting. It's just a heating curve. Yeah. Okay. Yes. Okay. So if I am, which direction on this little diagram, which direction is exothermic?
Going left.
Correct. Going left is exothermic. So the changes going this way are exothermic. That means condensing and freezing, or it doesn't show it on here, but deposition is going from gas straight to a solid. And that's because the system would have to release its energy in order for it to go to the next phase down. Because what happens is, as it's releasing the energy, you're forming stronger intermolecular forces. Yes? Iodine can. Carbon dioxide. When you freeze carbon dioxide, it goes straight from the gas to the solid. And then, consequently, when you heat it back up, it sublimates and goes straight from the solid to the gas. We tend to think of solid to gas more often because it's more common, sublimation. Like dry ice, that's CO2, yeah. Or like, like if your grandmother has those, like grandmothers like those little air fresheners that are like that solid little thing, and they put them in the bathroom and then they dissipate to nothing, that's also sublimation, yeah. But deposition is the opposite. But iodine will do that. If I heat up iodine crystals, it goes straight to a gas and then it condenses straight back down. Yes. Yes.
Why does the gas do that? Why does
It has to do with the vapor pressure and the triple point, and it has to do with their vapor pressure and what their normal melting or boiling point is. They're fancy. That's why. No. It has to do with their vapor pressure and stuff. And then, of course, if this way is exothermic, then the other way is endothermic. So any changes happening that way are endothermic, meaning we have to put energy into the system to get them to happen. So if I want ice to melt, I have to put some energy into the system and heat it up. And then ice melts. Okay. When you are at the specific areas, you're going to use different formulas to get how much heat is involved. So if you are at where one of the slope is increasing, thus we're going to use the MCAT equation, because you're caring how much the temperature changes, you're caring about the mass, and you're caring about the specific heat. Notice on here, the specific heat of ice, water, and steam are different. They have different values, so you would use those specific heat values. But if you are at one of the flat lines, then the first flat line is the melting freezing line. Then you would use Q is equal to the heat of fusion times moles, or you could do times grams, depending on what your units of heat of fusions is. Now, if you're doing fusion, that means you are melting it, okay? So your value would be positive. If you are freezing it, you would still use the same of heat of fusion value, but you would change the sign, because now it would be releasing that much heat in order to freeze. Same concept at the heat of vaporization mark, which is the boiling condensing line. If I'm going forward, it's going to be a positive delta H, but if I'm going reverse, I would change the sign of my delta H. Okay? Does that make sense? All right. There's a whole lot of questions down below, but they're already answered, so I encourage you to read through those. I don't think there's any that I can think of off the top of my head that I wanted to make note of that we haven't already talked about. Other than, hopefully you know that these are chemical changes when you're phase changing. Or the physical changes. Oh my gosh! Physical changes for phase changes. What did I just say? That's why you don't go on autopilot. Physical phase. Physical phase. They both have a pH in them. All right. The end.